Okay, so yeah, so one of the packages that I've been working on a lot is very related to some of the things that Alexandre was talking about, for example, which is what happens, what can we do with constraints? So what do we mean by constraints? Basically inequalities, and this is related to global optimization as well. So we have the interval constraint programming package, and there's a package called interval optimization.jl, which is actually pretty empty right now. I mean, it has a very basic implementation of a basic method, but I have sort of been working on more interesting versions of packages. So what do I mean by constraints or inequalities? Just things like x squared plus y squared less than or equal to 3. So that's some set in the plane, the set of all x and y that satisfy that inequality is some set. We know that it's actually a disk. And we want to characterize that set. So we want to just be able to say, is a given region, does a given region, say a square box or a rectangular box, does that box lie inside the set, or does it lie outside the set? Or maybe it lies partially inside and partially outside. And then similarly, when we want to be able to solve equations, so we want to, that's what really we mean by solving an inequality, is finding that set. And this is a special case. If we replace the inequality by an equation, now we have just a standard kind of equation that we're all used to. So here's a nice nonlinear equation in one variable, or if I put a y here, it's in two variables. And then you might want to find, the solution curve or whatever. So it's either, if it were in one variable, it would just be roots. If it were in two variables, it would be some solution set that is going to, in general, be some kind of curve. And note that these are declarative specifications, right? How do you solve an equation? How do you solve an inequality? It's a hard problem. And so what we need to do is take these declarative specification and convert it into algorithms. And we're going to use contractors, as Alexandre was, Julien, sorry. I'm not sure how you like to say your name. We need to convert those into algorithms using contractors. And so recently, the main emphasis has been on, the status of the, the status of the package is that I rewrote interval constraint programming to use the great new symbolics.jl package that I just showed. So this is really a game changer in Julia. It's a fast symbolic manipulation toolbox written in pure Julia. And so as I showed, you can just pass in symbolic variables into Julia functions and you get back a symbolic representation of the function. And that's what we need to do all these algorithms that take a sort of structure of an equation and they decompose it into pieces and then put those pieces back together into algorithms. So previously, in order to do that, you needed to use macros. So that's what I was doing previously in interval constraint programming, and that's what is used in Taylor models, in Taylor series, etc. So macros, however, have a big problem, which is that you have to actually, when you define your function, you have to use a macro to define your function in order that it can then be split up later. And that is, it was actually Marcelo who first, basically asked, is there a way to, I want to do a computation and end up with basically a Julia function or a kind of an expression, and then use this package, interval constraint programming, to basically draw, find sets associated to that expression. And macros don't allow you to do that. And so we need to get away from macros. And symbolics enables us to do that, to get the structure of a Julia expression. So I just want to show a couple of examples of what we can do, or what this looks like. So here is one example. So here's some actual Julia code. And what it does is define.
Where's David?
David.
Yeah. Sorry, wrong.
Yeah, but it's in your slides. Huh?
It's on the wrong screen. Yeah. Thanks. So here's how to use it. So I set up X, Y, I'm going to draw some pictures in 3 dimensions. So I have 3 variables, X, Y, and Z. I have a box in 3 dimensions from minus 2.5 to 2.5 in 3 dimensions. And now here are my expressions. And I'm passing them into these separator objects, or I could also just write now constraint here. So I'm not going to really go into what a separator is, but it's, actually maybe I will a bit. but it's a couple of contractors that tell me whether I'm inside or outside this set. Basically, it's an algorithm. So I'm generating an algorithm by doing this. Here's my symbolic expression, and I pass that into my thing that creates the algorithm. And now I'm paving it. That means I'm basically taking boxes and I'm splitting them up, and I'm checking it if each piece of the box is inside or outside. And then I'm just going to plot the result. And this is what it looks like. Of course, I cannot see anything. Here's my window. Everything was so carefully set up. Oh, I see. There we go. Okay. Hold on one moment. So here is the result. So this is plotted using Maki, which is this great 3D graphics library in Julia that uses OpenGL. So this is the twisted cubic. So this is, one surface in green, one surface in blue, and the intersection is this set here. And I've just made the boxes really big so you can actually see it. But of course, I can reduce the size of the boxes, and then you just get basically a curve. And this is, these boxes are a guaranteed over approximation of this twisted cubic curve. That's the intersection of these two algebraic surfaces. And let's look at another example. Here's a triply periodic surface given by this expression. Cos x times sine y plus cos y times sine z plus cos z times sine x equals 0. And so I'm doing the same thing again. And now I should see, of course, I don't see it. I've been having some trouble with the visualizations. I had it a minute ago. Sorry, one moment. It's pretty nice. So I want to. So it's just computing right now. It's a pretty heavy computation. There we go. Okay. So there is my triply periodic surface. So again, this is an over approximation of the surface. So these are tiny boxes, which are all cubes, and then they're enclosing this triply periodic surface, and you can rotate it around and get it in. I haven't understood how to rotate it properly either, but anyway, you can get the idea. Okay, so how does this all work? So let me go to the other presentation. Okay, yeah, so what I'm doing is constraint programming. Where is my, there we go. It's not at the right. Sorry about this. I don't understand what's going on. Let me undo that. Okay. So what is a constraint satisfaction problem? It's just what I was just saying. Basically, you can write it down formally, but it's just you have a set of inequalities that you can also think of as just constraints, and I want to find the set that satisfies those constraints. And so I've just given these examples, and so again, here's symbolic variables, and I can just literally write down this symbolic expression x plus y plus 2z less than or equal to 3, and I get this symbolic representation of this constraint set. And now what I want to do is pass that in, as I said, to my package, to this separator object or a contractor object, which will tear apart this expression and convert it into an algorithm that basically I can feed in a box and it will test, does that box satisfy this constraint or not? Okay, and then the latest developments are using that for constraint optimization, which of course is currently not working because I had a problem with the code, but this is what it should look like. So I should just be able to set up a constraint optimization problem, just like if you've used the differential equations package in Julia, you would set up a differential equation problem. And many other packages do this as well. You just sort of define a type which is going to collect all the data for your problem, and then you define a solve method to solve the problem. And so you can actually write, this very kind of nice syntax where I've already defined my symbolic variables, and so I just say the set of variables in my problem is x and y. It's a standard Julia vector. The objective function is just this symbolic expression. And the set of constraints is some set of symbolic expressions listed as a vector. And then the domain that I want to optimize over is this. And then, I did actually have this working. And so you can solve rigorously this constraint optimization problem using contractors and using this sort of well-known kind of Morse-Skilbo type algorithm for global optimization. So this is going to give me the guaranteed global optimum of this constraint optimization problem. Of course, it's a very simple one. It's hard to solve these problems, but it's a shame that it's not working right now, but it basically works. And you can see that if you're used to some modeling language like Ample or Jump, it's very similar, except that this is not a modeling language. That's the point. This is just Julia code. But I'm using these symbolic variables to give this sort of feel of a modeling language with no macros, right? There's no macros here at all. So that's the sort of new idea about how to do this symbolic modeling. Okay, so then I can plot and everything and solve the problem. So solving would be sort of, here's my problem object and I call the minimize function, and it's going to compute the global minimum and the minimizers, and it does all actually work, and I promise. Okay, so this is not yet in the interval optimization package, but of course it should be included there at some point. I've now lost the screen where I had the chat going on, so if you have comments, please just say them out loud. Okay, so here's another example. So because I have these symbolic objects, I can also just define, define an objective function. Here's a Julia function. And then by passing in the symbolic object, again, we sort of trace this symbolic function and we get a symbolic object back. Trace the Julia function to get a symbolic object back. And then I can just pass in those objects just like this, right? So I previously defined all my objects. Now I'm passing them to this optimization problem object. Okay, so how does interval arithmetic characterize constraint sets? So here's a sort of generic constraint set. It's just, I have some function C of some number of variables, and I want to know, the set is those x such that C is less than 0, and I want to find which x are in that set. So I want to be able to pass in a point and check if that point is in the set. Well, that's easy. I just evaluate the function at that point, at that single vector. But if I wanted to do more than one point at a time, I want to characterize sets, then I need interval arithmetic or some other, or lazy sets or some other set computation package. So how does interval arithmetic do it? Well, here are some boxes, and I can just, here's my standard Julia function. Of course, I can just pass these boxes straight into my Julia function. And for example, C of y1 is -1 to -0.5. This is just normal interval arithmetic, except now I have interval boxes, which is I haven't mentioned before, which are in higher dimensions. And so you just pass that into a function that takes a vector. This is a vector of intervals. And then it all works, and it just does standard interval arithmetic. And so, for example, here you can check, is this set a subset of -∞ to 0? It is. In other words, the result lies completely below 0, and so the box lies completely within the constraint set. And so here's a picture of the constraint set. So this is computed using the package, this disk. And then here are these boxes that I'm computing with. And so this is the one we just proved is inside. This is similarly, you can prove this is outside. And the problem is this box, of course, which crosses the boundary. And so part of it is inside and part of it is outside. And so again, we would need to return this sort of interval 0, 1 or Boolean 0, 1, Boolean true, false, third valued logic for this set. And so can we do something better? And the answer is we can. We can do contractors. So what is a contractor? I'm just going to jump to the picture. I'm not going to go into the details. I've talked about that a lot in previous JuliaCon talks, etc., how this actually works. Here is the picture. Here's my input set. And what I'm going to be able to do is define an algorithm that contracts this box. So here's an input box, and I apply my contractor that's based on an algorithm that I created based on the symbolic expression, and it reduces it to this size, this purple box. So it has removed the piece of the box that was outside the set, where it proved that this part of the box was outside. And then I can do the same thing with what a separator is it does that outside, and then it sort of reverses and it looks for what is outside the complement of the set. In other words, what is inside the set. And so in the end, I get this picture. So I can prove that this piece is outside, and I can prove that this piece is inside. And then this piece is sort of on the boundary, and I don't know whether it's inside or outside, and I will have to bisect more to find out. And so these are, so where do these contractors come from? They come from, as I said, the expression, right? So here's the expression that I'm looking at, x squared plus y squared. And what I'm doing is taking it apart and putting it back together again. So I'm basically, I can think of the expression tree or computational graph of this function. And at each node of that tree, I'm going to create a new variable. Here are the variables. So this is actually generated Julia code. This is one of the great things about Julia, is that I can generate code in a sort of relatively easy way. So this is actually code, but I can do the same thing with just symbolic expressions now using symbolics.jl. So I can basically have a sort of symbolic version of this trace of this function. So the first thing I do is, x squared, and I call that some new variable L, and then y squared is a new variable M, and n is L plus M, so that's x squared plus y squared, and then I intersect that with the constraint. And then the key point is that I need these reverse functions, which are basically sort of inverse functions for these things. So what does it mean to take the inverse of x squared? Of course, x squared is not it's not injective. There's more than one value gives the same square. So it doesn't make sense to talk about the inverse function, except that because we're in this world where we have sets, I can actually talk about the inverse function as just a function mapping a set to a set. So actually the correct way to think about this is as that this is a relation, not a function. And then just talking about the inverse or transpose or converse or whatever you want to call it of a relation. And so there's been a lot of work on relational interval arithmetic over the years. And so these functions are contractors that are implemented in the interval contractors package in JuliaIntervals organization. And that's what we're using. And so that's what this rev calls one of these contractor functions, and which basically does this kind of inverse operation. So the inverse of plus is basically minus, and the inverse of square is basically square root, but you have to do it in the correct way to take account of the different pieces, etc. So it's actually pretty annoying. It's pretty badly documented how to do this. And for example, the standard, the interval standard that I was talking about before, does not tell you how to implement these functions. And it just says you have to implement them, but it doesn't say how to do that. Right? So it's and that's actually not so obvious. And there's probably still quite a few bugs in those functions that we need to fix. Okay, so that's the basic idea. And so what's the status? So I'm just going to wrap up. So the status is that basically all of this works in a branch called rewrite. And then there's another branch called parameters that I think now exists, where you can actually parameterize these constructors in order to do global optimization. So I like this, just going to finish with this visualization. So here's a visualization of the global optimization algorithm using interval arithmetic. So here's my function, and I'm trying to find the global optimum of this function over this input box. So I have a visualization here that of how the algorithm works. So I'm looking at the box in red all the time, or orange, And what I'm doing is evaluating at the midpoint of the box. And I'm saying, is there a lower value of the function, right? And here, so currently this, and this green dashed line is the upper bound of the global minimum. And so I'm going to evaluate here and say, is there a lower version? Yes, there is. It's this down here. And so at the next step, I'll decrease my global minimum to that point, right? So it was here. Sorry. It was up here, the upper bound. And now, well, the upper bound has to be above any value of the function. So I found a value of the function and I decrease the upper bound there. And now I'm looking at this box. And then after I evaluate a box, I bisect it. And here I'm evaluating this box, and the midpoint value is above the current global upper bound. And so I don't do anything, I just bisect it. And I carry on bisecting until I get a box like this. And this box, using interval arithmetic, so this is a picture of interval arithmetic in action. So here is my function given by x times sine x, which has this dependency problem. And you can see that the output of the interval arithmetic over this input box lies totally above this green line. That means that I know that the global minimum of my function, I've already proved it's below this green line, so it cannot be inside this box. And so I'm going to just delete that box. There it goes. So I have removed that box, and that's how I'm going to keep on doing that, running the algorithm, removing boxes and bisecting and decreasing my global minimum. This is a very well-known, simple algorithm to program called the Moore-Skelbo algorithm from the mid-70s. But rarely has it been visualized before, possibly. So, and you can see that, okay, it started creating these clusters of boxes around these minima. That's a problem with these global optimization methods, is it produces clusters of boxes. But actually now, at the next step, you can see that, oh, it actually discovered that there was a piece of the function over here. And now it's going to go and clean up all those functions because it knows that those boxes, because it knows that those do not contain the global minimum. And now there is the global minimum over this input box. So now you can do this constrained as well. So this is unconstrained optimization, but if you have constraints, then you use contractors and separators to prove whether your box satisfies the constraints or not. And you include that into this algorithm, and that's what I tried to show, but was not quite working right now. And so all of this, constrained optimization, as I said, should be included into the interval optimization package when I have time, basically. Okay, so I don't see the message in the chat, so probably it's time for me to finish. So it's very exciting, very beautiful ideas, and Julia makes it, possible to do nice interfaces and use these. I think, as I said, this symbolics package is really a game changer for these kind of tools. And for example, Benoit is going to talk about interval root finding, and we need to mash these packages together so that you can use these contractors to more efficiently find roots as well, for example. Okay, thanks very much.